Yeah, hello. So, first of all, the observation that I'm seeing less than half of the people that I think was in the class. Yeah, that's another thing. It would be great if you guys showed up. I'm just gonna say this for the video because I know there are people in there that are just watching the videos. It's more fun coming to class. Hello. Great, thank you. Cool. So another thing is, how was buffer lab? Maybe that's why I'm missing people. No? It was okay, not too bad, terrible. I have no idea what you're talking about. You have no idea what I'm talking about. No. Yeah. You.
I yet can't find the readings for the knob sleds. I had to like Google search it. I can't find them.
Oh, you mean like to read ahead of time?
Yeah. No, for like.
Oh, in general.
Yeah.
Ah, yeah.
Like there's no place.
So here's the thing: is there's a lot of really bad content out there. Right? Some of it is in the underground, but I can try to question some readings. But the book itself that comes to pass has a chapter I think on obstacles too. And today's class is about obstacles too, so that'll be fine. Any other comments on this? Look at the scoreboard, how it went, huh? So we have browser here, buffer lab, buff lab. So let's try it down here. Ta-da-da! Yay! Actually, so let's, oh, wow, it doesn't work so well. Let's put this here, computer, laptop. So, here is the scoreboard. So let me see, 3, 6, 9, 12. There's at least someone in here who didn't complete everything, right? Usually it tends to be all the people that do really well, they're the ones showing up to class. Right? For those of you who didn't do all of these, I guess all of you made pretty much everything. That's great. Okay, this is actually good progress. But nobody hacked the scoreboard. What's up with that?
I couldn't find the method that was mentioned
The method?
in the lab because it said this particular method. It's called. I couldn't find it.
It was a hint for like many leaps ahead of like what you're supposed to be doing, right? So it's a Perl script, so it has to validate what you submit to it. And therefore, it executes all your code. Therefore, if what your code executes gives you some sort of shell, then there are several ways in which you can proceed. One of them is that you can try to create like an open socket and connect to it, and that will definitely kill the Perl script, which is bad. Or you can just create a shell under the permissions of the buffer lab user in some location, and then you can execute that and become the buffer lab user, and then you have access to all their stuff and all their processes, and then there you can start modifying the Perl script. Maybe the hint was just throwing you off. I added it there just to make it simpler, but apparently that wasn't the case. Because this is the first year nobody hacked the buffer lab scoreboard. Usually this is completely tainted by now. The pictures and what. So yeah, there's a very kind of civil approach to hacking. But in the future, when I have these open-ended assignments, they actually do involve a lot of work. They're supposed to be fun to have extra time to get. Which we all can do, right? Yeah. Anyway, so getting back to talk, any comments on this exercise? Was this kind of, how many people thought it was too easy? How many people thought it was just right? Okay, how many people thought it was in the harder kind of caliber of things? Okay, that's good to know. That's actually good feedback. And then all the empty seats, I don't know what they're saying. We'll try to read into that somehow. We're going to be moving now to projects that are going to have shorter write-ups and more hands-on stuff. These are kind of assignments you won't be able to Google at all because they're just my stuff. They're all going to be on Triton, so they're going to be local access to Triton. And I've opened up the next one, so let's talk about that one at the end of the class. It's due next Friday, so the 30th September. There's going to be 4 stack, or like 4 stacked buffer overflows that you're going to have to exploit with various different constraints. Cool. Anyway, so what I want to talk about today is just to recap a little bit what we did a week ago. This is about exploitation. Just kind of go through again an exploit because it's a little bit new when you see it first, and it's good to kind of just get it oriented. And then we'll talk about some of the things that can go wrong and how we overcome them as hackers. Okay? So remember that this is the type of typical situation. There's some buffer, and there's some string copy or something, and here's the assembly code that's here on the right-hand side. And what you see is that even though we request 128 bytes for buffer, what we actually get is, in this case here, how do we find the actual true size of the buffer? Well, look at the assembly code, it's over here, and you look at it, it's like, the way this buff thing here is used is that it's the first argument to string copy. First argument to string copy is the last thing that's pushed onto the stack before calling it, which is this EAX thing over there, which has the value of OX88 away from PDP. So there's some frame pointer, and then OX88 bytes from there. There's the beginning of the buffer, and then you would write it towards it, which means that after this many bytes, OX88, you would reach the old frame pointer, and then after that you'd reach the instruction pointer. And now, how is our calculus today? It's even the same number as that. Fine, I'll use a better word. How is our numeric skills today? Can we figure out what OX88 is? Let's do it on Monday.
7 plus 8.
Which is?
128 plus 8.
136, yeah, exactly. OX80 is just half of OX100, which is 256. So it's 128, and then you add 8 bytes. Okay? So it's 136 bytes, even though we requested 128. So that's something to keep in mind. So we have to put in 136 bytes, and then the next 4 bytes are going to be the, if I keep overblowing beyond 136, the next 4 bytes will override the saved frame pointer, and then return this. If I just overwrite the next 4 bytes, the saved frame pointer, what kind of errors or faults should I be looking at? What will I see? You'll see segmentation faults, but weird ones, right? Why are they weird? Why are they weirder than if I go even further and just overwrite my saved instruction pointer? In which case I'll get a crash saying like I'm trying to execute at OX414141 or something. Why are these frame pointer ones weirder?
The rest of the program depends on them, so you return.
You successfully return, right? And then you start to do stuff, right? And then you try to make some indirect retrieval of something, maybe be a legitimate address that you put in there, you try to pop something off a stack somewhere. It's just that it's a memory access rather than it being the instruction pointer, which is just like more obvious. But when you do the demask trick, you usually see that there's somebody trying to access memory at whatever it is they're putting. Okay, so let's just pop through over here. So we set up the stack from over here, and here's what things look like this graphically. We have the old frame pointer, we have the old instruction pointer, and we have the argument. And I was showing this to you again because there's something new I want you to see here, which is kind of looking at the stuff that follows even further than the old instruction pointer, the old stack frame. Okay? So we're going to subtract here, in this case, it's 98 bytes from ESP. So now our stack pointer starts over here at this green thing, and then it ends there at the base, at the old EBP. And we're now going to call this little operation, and we're going to shove into our stack frame at OX4. We're going to shove in the second argument to string copy, and then we're going to put in the first argument to string copy. Right? We took these extra 8 bytes just to provide arguments to string copy instead of calling push twice. So we set up the entire stack frame, including arguments for the next one. Then we have a start buffer here at OX88, and then it goes into here, followed by frame pointer, instruction pointer, right? And then at the very end, we're going to pop off, we're going to move the frame pointer, so like the first blue thing over there into our stack pointer, and then we're just going to pop that one off and return, okay? So at the very end, this is what happens here. This green thing here, we're now, our stack pointer coincides with the frame pointer, and then we pop off, so now our stack pointer is right here, and our frame pointer is whatever it was up here, further up to larger addresses. So far so good, right? Good. So, notice that the argument to the function, this vulnerable function here called vuln1, still exists on the stack, right? Where are they? whoever called this vulnerable function of ours must have pushed arguments right before the call was. So where are these arguments now? Still a stack, and immediately after the instruction pointer that we just overflowed, right? It's interesting. And this will become interesting in a different context slightly later, right? So, yeah, if we overflow it, this is kind of what it looks like. We'll get, say, BBB and CCGZ into these addresses, and when we restore, we get a set instruction point. So far, this is just review. Okay, so given that we have control over EIP, what we did last time was just to jump into either code that's already in the program. So it's like the Neverland function that just happened to be there and was really convenient. But that never happens, of course, right? It's Neverland. So instead, we jumped into some data that we control. And specifically, we jumped into the buffer itself, which was cool. Right? So instead of filling it with garbage, we fill it up with our code. And here's what we fill it up with a bunch of code, and then just follow it up with these instructions over there. Now, I mentioned that things became a little bit variable, that actually this buffer address wasn't so deterministic. I may have mentioned this in passing. Let's investigate that claim a little bit. So, at the very base, the first thing that's like pushed onto your stack in the program are the argv table, like the first arguments to the actual program, followed by the entire environment table. You guys remember the environment table that has things like user equals something, path equals that, home directory exists. Like all this information that's used by a variety of programs to do things like color highlighting and figuring out where my mailbox lives. These are settings, effectively. It's like a registry, a very old school registry. This lists at the very bottom of the stack. This also means that if it changes a little bit, all these stack addresses that follow are going to change. So if I suddenly add another thing to the environment and I run this overflow, my buffer location here is going to be off. It's going to change. In fact, it's so sensitive that when you run a program like the exploits that we've been running, if you run them just on the console and you run them within GDB, which adds an environment variable, your buffers are going to be mismatched. This is extremely confusing when you first do it. You look at like, this is the address, I'm looking at the GDB, and I'm showing it into my exploit, and it doesn't work, right? And this is why we want to build in some robustness into our exploits. So the idea there was to say, hey, let's create an upstep, right? Now the problem can be exacerbated even further, which is the defense part that we came up with. Remember the defenses we were brainstorming about? One of them was like, hey, what if we just like randomize everything? Why not, right? As long as the program is internally consistent and can find all the things in the libraries, then making things random sounds pretty alert, because then the attacker can't know where to return. Yes? So on modern systems, there is this thing called ASLR in Linux. And yeah, it's called ASLR in all operating systems, actually. If you look at the view of a program, or what the process actually looks like, here's how you can actually find it out. So there's a file called /proc/current process ID, which could just be self to identify your own process, and then maps. So this proc file system in Linux is something that's not actually a real file system. If you go into it, they're just a bunch of files that are all 0 bytes and so forth, but they're generated to give you a view of what's happening inside the kernel, the actual system. So in fact, you have a number of these files. Let's just go on and explore a few of them over here. So here's /proc, and there's a whole bunch of garbage here. And you go in here and you look at, what's inside devices? And if you look at this file devices, you see that it's just like this 0 byte file owned by root. It contains nothing. But when you actually open it and try to read it, it had all this stuff inside of it. It's like going inside one of these magic pens in Harry Potter. It's like, there's like nothing, you're like, that's amazing, right? That's the proc file system. It has all these information that is very useful. So if I just go into self here would be, as you can see, it automatically changes it to 23014, because if I look at who I am and I grab my shell here, I see that this is my ZSH. That's my, and this beautiful green over here. This is the process IP for my own shell. And inside here, you can get a lot of information. You can see things like mount info, like where are things mounted in my shell. I can get information about what I have open, statistics like ad nauseum, right? This is like data lust. Like you can really go all in here and find stuff. But you can find this file called maps. Now what's maps? Maps are all the memory that has been allocated. In particular, in this process, so every process kind of sees the same thing. All processes in the Unix system, they think the world looks the same way. They're all kind of very egocentric. They think that their process is located at 0x, 08, 04 or something. They think that their library is located at these addresses and so forth. This is all virtual. That's where we have virtual memory abstraction. So the kernel tries to strive to keep this separation, this isolation between different processes, so that they may all kind of like plunder and take memory and do all this stuff without actually affecting anyone else. If you try to write an operating system where everybody can like access other processes' memory, oh my God, it's going to be exactly like Windows. Right? It's going to be terrible. It's like DOS. It's bound to fail because of the lack of encapsulation, the lack of isolation. So anyway, this process over here has a bunch of garbage in it. All these pages that you're seeing right here, they're all library pages here. libc, LD. This is all the stuff that we need to access to be able to execute things like printf and so forth. So if you want to access printf, it's going to be located somewhere here, right? And here are the addresses. And you can see that these are actually 64-bit addresses. The things further up here, you can see are actually 32-bit addresses. So they include things like basic kind of basic sections that have been loaded from the actual file. Here's the heap itself. And you can see the heap is pretty big. And what you notice here, if you look at it, is that there are some bits on every single page. This is whether or not you can read this content, write to this content, execute this content, whether or not it's somewhat protected. I forget exactly what that means. Notice that you can never write and execute at the same time. This is a defense, often stylistically written as this. As W, X or X. Write or execute. Or sometimes called data execution prevention. We call it NX, non-executable stack or so forth. This thing here is also synonymous with a bit that's inside the CPU that says, hey, I don't want to have these things at the same time. So I specifically have to enable when things are going on. So that's one level of protection, is to make sure that things are never simultaneously in this bit. The other protection is actually evident in here if I go into a different process. Let's go into some other random process here. We're going to do 241. We're going to cat its maps over here. That was a boring process. 5272, cat maps. And what you may notice is that things are supposedly all over the place. Are they? Let's see. Proxies, kernel, randomize. Oh, okay. No, they're not actually all over the place. So what I just found here was a file called proxies kernel randomize VSpace. This is a file that I can actually write to. And when I write to it, I actually make changes to the computer. This is a means for me to communicate with the kernel and tell it, hey, that parameter option of randomizing virtual address space, yeah, it should have the value of 0. I just read it and it's 0. If I put it at something else, I've actually changed how the kernel deals with applications. So let's turn it on. I'm going to go ahead here and I'm going to say, this is sudo echo 2 to this file. I wish I had an end button here. Okay, let's try this. Command, okay, sudo best. Because otherwise, the wrong process is going to try to write to the file. And we want that permission. Sys kernel, and I'm going to silence that. Randomize kernel. Prox, yes, prox. Randomize VSpace, okay? ls, okay, so I'm going to just cat proc self maps, okay? I'm just for the self now refers to different ls instances. Notice what's happening here. You see that? Terms of these addresses are changing. In particular, everything here that's called here the stack, the VDSO, the heap up here. When I do this repeatedly, they're all in different places. Right? That means that on every execution, things are re-randomized. Now that's true for Linux. In Windows, it's actually not true. Because it's just at the beginning of the operating system, we get random segments, and then that's not going to change. It's kind of because of the way things are laid out on Windows. Which is a huge vulnerability. And we'll talk about that. Now, why am I talking about this? Suppose we're in 32-bit space here. This means that we need to be able to figure out information about where we are if we want to be exploiting things, right? So one of the things we have to be able to do is to know, for instance, that where our frame pointer is. So if I run this, for instance, several times here, and I just try to get the frame pointer, I'll see that if there's no address space randomization, it doesn't change at all here. But if I add a parameter to the program, it shifts. It shifts again. So we turned off address space randomization. We have a program, all it's doing is trying to get the current frame pointer, prints it out, and I run that program with no parameters, and then with a few parameters, and then with longer parameters, and then with more number of them. Why am I seeing these shifts here? What's going on with these three numbers? Can somebody explain them to me?
As it stores more parameters on the stack, it has to change the memory address and it has to increase it because it needs more space.
But notice, so how many more bytes were between here and here?
It's 3 times the number of bytes. It's 12 characters.
And the difference in addresses here is 16, right? And here, I had a bunch of small parameters. It's also 16. It's funky, right? Now, you remember when I told you about how the compiler and the processor really strive to have certain alignment? Well, here's 16-byte alignment, right at you, right? So if you add a few more bytes here, even a handful of bytes, it'll be like, it could be 16, it could be 8 bytes, we don't have enough information to do it, but it's certainly alignment, right? It's going to round up the number of bytes it's going to fit so that things end at certain boundaries. And here, there's going to be null bytes between every single argument. There's going to be an array of pointers, so each of those is going to cost 4. There's a whole bunch of cost in here, right? But this makes it extremely fragile. What's annoying about this is that when you're writing your exploit, you tend to be constructing that exploit buffer little by little. And as you discover more about your program and you add to your buffer, you shift all the addresses that you have previously pinned down. And that can be very frustrating. So it sometimes helps to just have always the same size of buffer and then just make modifications within it, because then you're not running into this problem. Okay, so here I'm also shifting things around by adding, wait a second, why wasn't that changed over here? I don't understand why these wouldn't be different. Variable name, blah, blah. That should be different. Maybe it got rounded up correctly, but that doesn't make sense. I don't understand why this is happening. The next one here, you have a whole bunch more of variable addresses over here. And that shifts it by another 16 bytes. Oh, okay. It didn't get exported. So it actually didn't become a part of the environment table here. Here we made sure that it's part of the environment table by calling export, in which case things get shifted around. It's odd though. So, well, as I said before, the things that shift things around include annoying things like what terminal are you running, what host name do you log in from. So if you have a screen or something open, or you went in and you ran your exploit and then you logged out and you went back in from a different computer, the number of digits in your IP address or the host name like that can actually affect your exploitation. It's really annoying. So to counter this variability, we introduced knob sliding last time. And that was a very simple technique. All we did was we just had the surplus bytes in the buffer filled with knobs, and we tried to jump in the middle, which gave us some kind of variability cushion, because we can hit any one of the bytes inside our knob side, and we will therefore execute our code. So it's like the simplest possible technique, right? More probability of success. So normally you try to go into the middle of the knob sled, if you can try to do the calculations. But in this case here, we're 96. Suppose we didn't have this. Suppose that this wasn't enough. That, for instance, maybe with really long shell code, we didn't have space for a lot of knobs. Is there anything else we could do to try to help determine these addresses a little better? Yeah.
Created knob sleds in the house
Where would you create it?
and the stack.
In the stack? This is all on the stack. Just you went somewhere else in the stack.
Yeah.
But we're on the stack.
Before we actually
Ooh, before you accept it. How would you get it there? What's at the very bottom of our stack?
ESP.
Yeah, so that's the stack frame. But the very stack itself, the first thing that gets pushed onto there are the name of the program and the arguments and so forth, and then the environment table. And we can affect the environment table. So why not show our little code in there, right? So here's a way in which we can just print out the environment table. You say like, hey, take the environment table here, print out the address of it, and as well as the number. So this is a program that just tells you that different things are these particular addresses. And this should not shift as much because we're not adding anything to the environment table. So barring any address-based randomization, you'll now be able to do something like this. You can say, hey, I want to export this thing called code. And it's supposed to contain these 4 characters, ASTF. You can run this program and you can say, hey, it's at these addresses. So now I run different things, export things, and it's stuck. Ah, very nice. So now you could just shove that code into, shove some knob sled of any length. It's up to you. You can have a very long knob sled into that variable, followed by your split code, and you're fine. You can even go further than that and say, like, let me clear out all this other stuff, this crud on the stack. I don't care about the username of the host and something like that. I'm going to execute this program, and all it shall know is not, followed by like exploitation code, right? Then you really pinned it down. So that's one way. And you would do that by just saying, hey, remember exec V8, we had this third parameter here, which is the environment table, which we put as null before? Well, it doesn't have to be null. It can just be our rogue code. Aha. So we can run it over here, and we know exactly where it's supposed to end up. So that's much easier to predict, right? And sometimes this is important because we need to be able to predict things on a remote system, or we need to be able to deal with randomization. So I think it's nuts all over the system. So here's what happens if you turn on that ASLR mechanism from before. Then if I run this program EBP, just to find the frame pointer, you get stuff all over the horizon. This is the parameter here, ASLR. So remember I set it to 2 instead of it being 0. So what does it mean? Well, if I put it at 0, it means that there's no randomization going on at all. It's the most efficient way to go. It's the least secure because you can very reliably predict where things are going to be in the memory. You make it 1, you start to randomize where the heap goes, where the stack goes, and the VGSO pages. Which means that shared libraries are going to go into random pages, right? We'll talk about pi in just a bit. Wait, there is. There's something about pi. Oh, it's missing. Here, I'll show you the full one over here. Randomize VA space, just to show you kind of the progression things. Oracle. That's not what we do. Here we go. Here we go. Number 0, no randomization. 1, conservative, so it's stack VGSO. So Number 2 here, if you put in the full mode over here, what this means is that every single time you call the equivalent of mmap, this is called BRK, which just says, hey kernel, give me some more memory, that will be randomized. So it's the least efficient, because now you have to have a mechanism that deals with moving things around and rerouting them. It's also the most secure, because now the maximum amount of memory that you have gets put in random addresses. This is important, because as you saw on the page over here, when I started doing this repeatedly, what do you notice when I do this repeatedly here? Some of these things change, some don't. The fact that some of these don't has been the biggest liability for security of the past 8 years. In particular in Windows, if you have a library, you have to specifically opt in to have your things randomized. And some things that don't want to be secure, like Java, they're like, yeah, I don't care. So if you have Java compiled with your binary, it's always going to be in the same location. So that means if you attack that program, you can always jump into Java code, because you know exactly what it's going to be. This has been a huge obstacle to Windows security. Another thing is that the base of your actual binary, so if you look at the binary base here, you see that there's this very top here, 00400, this part here. If I keep going up and down, this is also static. And that's because the binary just wants to be able to start executing an image where all of its main things are like this base location, and then everything else goes. If you want to overcome that and be able to randomize even the base of the binary, you're in a mode called PI, position-independent execution, meaning that you can execute wherever. It's going to have to figure out the relative offsets of all the different segments. It adds between 10 and 20% latency, or like penalty overhead, on the runtime of your program, which has been deemed to be too high to be default. But now what's happening in Linux and some others is that the privileged programs are kind of forced to have this extra performance over, because then you can randomize pretty much everything, which is cool. So now let me ask you, this is the defense that we have. What do we do as hackers about this defense? I actually mentioned 2, but let's just look at the average space randomization for now. What do we do?
Can you just disable the randomization?
It's something that only the root user can do. So we would always,
Because we have to get access to it.
yeah. So which is kind of the whole point of the hacking, is to get that access in the first place. So, or you can call them up and ask really nice of them. Yeah. This is John from Tech. Can you disable all the security defenses in yours? Yeah. You have no idea how successful that strategy really is. It's amazing. Like you think it will fail, and it like never does. Like you can actually call up and be like, yeah, I'm John from accounting, and I'm like, I need to administer a password on my computer. Oh yeah, it's it says that when you're talking to it. It's just it's amazing. Anyway, so where was I? Yeah, address space randomization. How do we overcome it?
Did you try and get EIP by using your exploit code? I think you gave a quick example of it last time, but like you call a function and you retrieve the EIP address.
But I retrieved it by looking in the binary and where it would be mounted, where this map thing would be. But every time I now would run it, it would be a different location. And that's the whole caveat, is that now I'd have to run it many times to get the location where I want to go. Now actually, if we're in 32-bit mode, like what I'm talking about, the number of addresses I have to try is actually not that big. It's only maybe a few bits of entropy. 8 to 10 bits, which is thousands of times, maybe 12. But for 64-bit, there's a lot more. So what would you do? Suppose you're in your hacker collective, or there's like World War III going on, and you're in that like special NSA unit that's trying to attack the enemy. What are you doing? Thinking about your life.
Use a pattern.
Choose a pattern. No, that's actually not a bad idea. We'll have a whole class dedicated to that here. Which is, are there patterns where none shall be found? Right? You put on a tinfoil hat and sort of look at random sequences and see some pattern in them. Because sometimes there are. We could do that. These sequences are seeded by something known as the pseudo-random number generator of the Linux kernel, which tries to collect all the information about how you type on your computer, all the timing delays between packets on the network, everything that it can, just like marches it together and stews it up and tries to create this source of entropy that is a little bit hard to defeat unless you really know what's going on. If you actually, and this is true, if you have a network device, it's just like a little thing that's sitting there on the wall, and it has no keyboard, it has no mouse, it has no way of really getting any input like that. The only thing it really has is like the packets that are going through it, which makes it extremely hard for it to create anything random, because we're all deterministic. Computers are deterministic. It has been shown that these devices are extremely predictable when it comes to figuring out their own random keys. I'll give you a little prequel of that. How many people are familiar with RSA? Exactly. Okay. So you know how RSA is like really hard if you have you have a P and you have a Q, like 2 primes and a gigantic, and this creates your thing around. Now to generate this giant primes, you had to have some random sequence to get there. Some people looked at it and be like, okay, it's hard to factor, but let's look at all the public keys, which includes this number n here, of all these different devices that are on the internet. Right? There's lots of SSL bits and so forth. And instead of running factorization, let's just run, so suppose this is some device 1 here, and like device I. Here's a device J here. That's another, let's give it names here. Let's just run GCD, greatest common divisor of Ni and Nj. Now you would expect that the primes are truly random, that this would be 1. They have no primes in common. So many devices had so little to work with to generate keys that they actually had a number here that was in common. And if they have a prime in common, what can we do now? Well, suppose we get we know that PI, which is equal to PJ, right? Suppose we get this. Well, then it's pretty easy to find Q from that. We divide N, right? And now we have the 2 primes. What can you do with the 2 primes in RSA? Yeah, you can find phi, so it's just P minus 1 times Q minus 1. That means that you can find D corresponding to the E because it's the inverse in that ring. And that means you have the entire private key, and you're good to go, right? So, pretty clever. And the reason that this is clever is because GCD is extremely easy to compute. It's it's one of the oldest algorithms we have, Euclid's algorithm. Whereas factoring, we have no idea if it's easier or hard. We just think it's hard. Anyway, that was a little aside here. So, can you come back, please? Hello. Ah, there we go. Okay, so that's one way. We can try to predict the sequences. I would say that's hard. The other thing we can try to do is to realize that while we're executing, these addresses are not changing. Which means that if you're attacking a service, and the service by definition needs to be up and maintain its own upkeep, like Apache or some web service needs to just sit there, wait for connection, and then spawn a new thread. And all of these are going to have the same addresses throughout the execution. Which means that if you get the term multiple times, yeah, you can try to guess the address. But if you have any way of leaking information about something in the program, like, oh, I give you a pointer, or in my debugging, I printed out %p, or there's some way for me to disclose any of the information internal to the program, that is information that I can use to try to figure out where EIP is or anything else. Okay. That's the way exploitation happens a lot today, is that we have this information disclosure bugs coupled with these overflows. Make sense? You can read sometimes more from if you're able to read a buffer longer than you're supposed to, then you end up with old information, which includes invariably pointers. Right? Like, you remember Heartbleed? Those types of information to close your books. Does it make sense? Anyway, suppose this is on here, and here's the state of affairs. So we have normally in 32-bit assembly, 0804 is kind of the base of where all the application stuff is going. This is where your code segment, this is where your program is, it's where it begins its life. like this particular address over here. Now, suppose we have this thing here, and we want to exploit it. And we have the additional drawback of not being able to inject our own data. We're overcoming the second defense that we mentioned. Okay? We're looking at this guy here. W X or NX or whatever you want to call it. Non-executable stuff. What can we do? This is a key observation. This really changed everything when it was taken to its fullest extent. What if you try to look at all the code that's in the binary already? What if there's useful code? The simplest possible example of that is, what if this thing that you're attacking already spawns a shell, right? What if it has system or execv or something just already there? Couldn't you just call that? You kind of ameliorate it somehow, or like adapt it to your purposes? Interesting, right? So let's have a look at this. Let's take another look at how things are before exploitation. So we have the string copy thing, which has our argumentaire CP, and then buff is the one that follows. We overflow stuff. Here's our buffer. Here's the end of it. We go to our frame pointer. Now we're about to call string copy, and then we leave ret. After we call string copy, according to its manual page, if we look at the manual page, it returns it returns a pointer to the destination string dest. So in fact, it returns, in this case here, the CP address in register. If I return something, it's an EAX, right? So EAX contains a pointer. It contains the address CP, right? That's the state of affairs before we do leave and write. Okay? And suppose that's the address. Suppose it has everything we need. Suppose it has the code that was copied. So then, let's defer this a little bit. I thought I was one slide ahead here. Let's defer. Suppose that we can inject data still, and we can execute it, but we don't know where things are. And string copy returns the destination buffer, which is by definition the thing that we copied our input into, and everything is kind of all over the place. What could we possibly do if we could select one instruction to run at this stage here? If our shellcode, like, to get to the right location would be one instruction long, what would it be? Does the setup make sense? It's a pretty random, but if you could choose one instruction, then you could get to the right destination. You want to execute the things that we injected into this buffer that's string copy worked on.
Where's the address in the EAX?
So how would you go to the address in the end? Hmm? Somebody gives you one instruction from x86, but you get to choose one. Yes, like a good prize. Yeah, and buy one of them. And that's the one that's going to get executed. And after that, you're on your own.
Call the AX.
Call the AX or jump the AX. Yeah. Either way, like somehow just move into AX. Now, the nice one is jump the AX because it's 2 bytes long, which is actually important. Why is it important? Because anywhere in memory where you can execute, the sequence of bytes FFE0 will be interpreted as jump EX, even if it were a part of another instruction.
Why?
Why?
Yeah, why does that is so important?
Why is it important? Because now when you overwrite your EIP, you just put it at the address 08048491. the CPU is completely oblivious to what was supposed to be in that address. It was maybe a part of another
And but
anything.
why did the CPU, when they set this up, why did they make it so that FFD0 was like so important? We'll just default to that.
Oh, it's not defaulting to anything. I'm just saying it's important because the probability now that somewhere in your memory that you're going to have these two bytes together, this will happen every 1 in 65,000 bytes if everything was random, right? So if I specifically put this address here, suppose this is at a fixed location in memory, this part here. If I just return to that, then what it will do is to execute jump EAX. Even though maybe the full instruction that was supposed to be executed was like V0 FFE0, which means something completely different. It's just, now we're in exactly this location, it will be interpreted as a jump EAX, and therefore we're going to jump into where our shellcode is. We don't have to find it, we just have to find this one instruction. It's a pivot point. Yes?
Why do you need to find this instruction? So doesn't the CPU automatically make everything even, so if by definition
Yeah.
by
On RISC, that's true, sometimes some RISC processors, because everything is before byte boundaries, but then you have the same thing. In Intel, x86 assembly, the instructions have different lengths. And the CPU has no way of telling that how many instructions were put in what location. You could have a call into the middle of a function. Now, it's a good idea. Maybe we should have it so that whenever you do a call, it should be at 16 byte a line or 8 byte a line. But because of all the legacy of what Intel has been doing in the past, what?
It doesn't do that.
It does not do that at all. You can, just like we were doing in a shellcode, you can call ahead, which is like, call 5 bytes, 6 bytes after, and so forth. It really has no means of knowing that it should be skipping. And it would actually add a lot of fragmentation that it's trying to avoid very frantically. So yeah, so anywhere we can find this stuff here, you're good to go. Now, of course, something to think about is there a protection mechanism that should be here to try to protect against it? And people are currently, today, speculating about something like that. And everything that's been proposed has been shot to pieces by us, the hackers. Right? So there's this convenient tool here called MSF LScan. It's a part of something called the Metasploit framework. This is what all our modern script kiddies use to try to break into places. And you're going to say like, hey, I want to find a jump to EAX and this vulnerable library, and it's going to say like, well, this thing here is a call to EAX, and this one here is a jump to EAX, and here's another one like there's a push and then a ret. This is another way of jumping to EAX. Right? And all these addresses make sense. So if any of them are at the memory location that's not randomized, so if we don't have pi, this position independent execution, this pivot point can get us there. So even if your stack is randomized, your heap is randomized, but there's this one instruction at a fixed location in your base binary, you can hack it. Makes sense, right? How many people think that this makes sense? Okay, we're reaching a majority here. I don't know what to read into like the like 1/3 half. Is that 1/3 vote or do I run it down or up? Uh-oh. We'll just sum it up. What is there anything that's unclear here? Something I should explain better here. Should I just walk through the steps a little bit? Just gonna.
So you just have to find these 2 bytes somewhere
Yeah.
in the code.
Let me just
And you
draw.
can jump to it.
Let me draw a picture. Here, right? Okay. Okay. So we have our binary. Okay. And there's a stack somewhere, but it's like totally randomized. We don't even know where it is located. Of course, this is all a continuum. There's a heap, and that's also located somewhere, but it's all randomized. These are all random, right? But then there's like a base that's in a very fixed location. This is fixed location. Fixed, maybe it's pinned at 0x 08 04 4000, something like that. And we have our string copy, and we know our string copy is it's executing somewhere, and it's going to copy things into like some location here in stack. We don't know which one it is. So we can't really guess the address when we override our instruction pointer. So instead, what we do is that when when we override our buffer, here's our state EBP and our state EIP. When we override these things, we can put whatever we want into the frame pointer. And into EIP, we're going to jump into a fixed location that has the bytes FFE0, which is equivalent to the processor thinking that we want to jump to EIX. Which EIX now points to where string copy pointed to, so we're now going to execute this, and then we're going to start executing over here, even though this was in a completely random address. We bypassed the whole random aspect. Make sense? We have affected a chain now. Instead of going directly to our shellcode, we jumped into a pivot point that found our shellcode for us. By simply reusing a register where things were already located, the EAX. Cool, huh? Makes more sense? Great. Yeah, so this is the summary of the technique here. Put the exploit code in the buffer, override the return address with that fixed location, ret. Now it's going to jump the EAX part, and that's going to jump into our EAX, which has been filled by the string copy, and now that's reliable. Very cool, huh? So that's called the jump to register technique. This is ubiquitous in Windows. It's very commonly used there when you see Windows exploits. And here's something that I think I forgot to mention. You remember how we were always fighting with these null bytes in Linux? So that curse doesn't even enter the picture in Windows, because Windows uses Unicode by default. The Unicode characters are always kind of 2 bytes. And one of these bytes, in almost every circumstance, is a null byte. So it doesn't stop at null bytes, it stops at a double null byte. So like, you're almost always good to go. Windows is just like, I mean, it's just too easy, so that's sort of big. Okay. So anyway, that's that part here. So I want to actually follow it up with development of the second part that I just mentioned. So let's do that. It's called, which is to deal with this specific instance of what happens when you can't actually execute the data you wrote. So right now, we're still relying on the fact that this dotted line over here, this, what's the yellow region here, so this region here can have our shellcode and we can execute it. But what if we don't have that? So I've been posing this question and I'm kind of like mysteriously walking away from the answer. But let's answer that. What can we do? So what I mentioned earlier was that, what if there's already code in the program that we can use? Currently, we just did a little bit of that. We just had a jump thing here. But what if there's something like execve or system or even Neverland or something like that? That's very useful. So let's have a look at what that is about. And this actually represents the beginning of a shift that has happened, which is called code reuse. This is the way exploitation is done today. It's more to use code reuse. The first of this is called Return-to-libc. So going back to our old picture here, we have our stack and everything is good to go. We have our pointers. And remember that the vulnerable function that was called, its arguments are still on the stack, right? We have argument 2, then argument 1, then EIP, EBP, so forth, going right to left. That means that any function here that wants to access its own arguments is always going to look at its current frame pointer and go 8 below it, 12 below it, 16 below, above it. Okay? So now, we're about to leave a function. It's done whatever it wants to do. It's not going to move EBP to ESP. Oh no, we're going to pop EBP, and all that's good. Now suppose that instead of returning into shellcode or into the place where you were previously, what if we return into the beginning of another function? Kind of like if we wanted to do a call. Suppose we wanted to just return into system, like the function that says system and then whatever argument. What would system think about the state of the world? What would it look like? So replace the EIP with the address of the system. Okay? Of course, system, like anything else, is going to expect its arguments to be at those locations. Are they? Of course, nobody ever actually called system, so it's just gonna look at the previous arguments that were to the function that we overflowed, or whatever we put in here, right? Because we can keep overflowing normally. You can overflow EPP, EFA, and then just keep going, and these things are not going to be interpreted as arguments, right? Does that make sense? So let's have a look. We're going to try to find some interesting function. We already found it. It's called system. We're going to prepare its arguments in the stack, and then we want to return to it. Use the instruction pointer to return to it. So here's system, and normally you do something like system/bin/sh, right? Why is this whole thing useful? Well, it's because in many cases libc is still at the fixed location, or like I was saying in Windows, there are libraries where things are always at the fixed location in memory because they haven't opted into data execution prevention. So this might be useful. So here's what we're going to do. We're going to put in here the address of system for our instruction pointer, 4 A's, and then the address of the string bin. Why do I put these A's in?
It's a local because you have 8 bits and you only need the bin, so we're trying to tell the code that you only have one.
Why wouldn't I put the bin thing into argument 1? Or what was previous argument 1?
Let's go the other way around.
Well, it's still the only argument. You know, the last argument is the one that goes last in. Like, why is it shifted like this? What's the difference between returning into system and calling system?
The calling system would increment the stack pointer by 4.
Yeah, it would call in and put its return address, right? So normally, if somebody were to do this legitimately, there would be another address over here, right? So there would be some old EIP of where we're going to next, and then you'd be living here with EVP, and then this would be the first argument. And everybody would be happy, right? But we didn't do that. We circumvented all that stuff. So we need to have this filler thing in here so that 8 EPP is here, right? Ah. Cool, huh? So now the question is, how do we locate a bin-h string? That should be fun. I want ideas. Back row? I can see you. Anyone? You could put in the, probably there's in fact something in the environment table, like shell equals, right? You can even put stuff in there, right? You can just put in the string bin anywhere. It doesn't have to be executable. It's just a string, right? That needs to be read. It can be anywhere, which is the beauty of it. And in fact, it is already in there in several places, so that's kind of convenient. In fact, it's in there specifically because what the system does is to open up bin-sh minus C, your argument. So it exists. We just need to put a pointer to it. But if everything's randomized, then we need to be a little bit careful, right? We'd ideally be able to find it either by finding an address in memory where it's pinned, like in the epilogue, or to generate it somehow, like know that it's at this particular, it's in this register and get it from a register, or copy it in from your buffer, or like some way in which we can obtain it, right? For us, we're going to do this. We're just going to put it in the buffer itself. So now instead of having shellcode, my shellcode contains it of the string bin-sh, and then a whole bunch of nothing, and then the frame pointer, doesn't matter what it is, the old instruction pointer thing, and then pointer to bin-sh. So here is supposed to be system. Okay? All good? I have no idea how to read this. It's okay? Should get like this green hands or something where you can like give thumbs up, thumbs down or something. Or like buzzers, like don't understand. 3x and I'm out. This plan makes sense, no? We're trying to put in system, you have a question?
Yeah, how'd you, I mean, if this is the first code you're running, how would you put, don't you need JSH to like make this code work? How would you put it in beforehand?
Well, it's supposed to still our overflow, right? So it's still a control over what we put in this buffer.
Okay.
So that buffer, like at the beginning of our exploit, instead of just putting in a fill or an ops or whatever, we're not planning to execute any shellcode. We're trying to reuse the system functions already there. So we're trying to provide our shellcode as an argument to it. And then we put all our magic there at the end. All right? So this is the case. What are some of the potential problems we're going to run into? I'm putting in the character /bin/sh. Tell you what, let's just give this a spin. Let's just try to implement this, okay? That's not a Putty terminal here. Okay, we have this beautiful thing called libc, and it's a very similar target practice program to the one week before. It has Neverland, but Neverland is actually never useful. What does Neverland do? It executes not useful, which is by definition not useful. Or it could be useful, but it's not useful. It has some other stuff, but the reason why it has it is because now instead of target, there is a reference to system. If I've taken like execve or something like that, it's going to say like, oh, it's somewhere, like it's not even a symbol that I use in the program. I'm just forcing there to be a symbol in the program. So we still have our target, but our target now has non-executable stack, non-executable heap. Ooh, can't do our old tricks. I'm going to fail. But we still want to exploit it. So what are we planning to do? We're planning to say, hey, target, I'm going to print 136, actually, how big is the buffer here? Target, let's see, 128, and let's look at this as copy argument. OX88, so it's the same thing, 136 A's, and then follow that with BBB, CCC, and let's see where we land. Segmentation fault. Okay, so this is good. And here, instead of going to the beginning of the buffer, we want to go into where? What do I want to do?
System?
System, how do I find system?
MS FDLs, ASLR.
What was that command?
I was trying to use the scan function that you use to scan through.
Oh, MSF lscan.
Yeah.
Lscan is finding particular kind of assembly commands around. It may have parameters for finding particular functions, but normally we just use GDP or object dump, something like that. There's also a Python code that I can show you that just like retrieves it for convenience. Okay, so here I've gone and I've actually found system at some nice location. What do I type? I can't hear myself. There's too much noise.
English down to the stack address.
So what do I do? First this one out, 64, 83, 04, 08. Okay. Oh, sh libc start main command my fun. What's happening? Can somebody explain what just happened?
It's not been linked yet.
It's been linked. In fact, the shell actually ran and is trying to run the argument libc start main. Here, I'm going to try blowing your mind a little bit. Oh, darn. I'm just having fun here a little bit. Let's see. Trying to see if I can hack it regardless. Okay, where's this? Where's this? Stats. Bin. Okay, let's see. Oh. Never mind, didn't work. I was gonna just try to see if I can force it to execute something that it wasn't supposed to, but it never actually bothered. Oh, bin. Ymir bin. Huh. Okay. Sorry, I'm having too much fun here. ln. Let's try the target again. Uh-oh. No, still doesn't work. Okay, it's doing stuff that is beyond our control. Anyway, it is calling system, because we returned it to system, but the argument that we provided to the system, we didn't provide anything, so it must be reusing something that's already on the stack, which happens to be the string __libc start main and some other stuff. Which is kind of cool, but what do we do next?
Put /bin sh in the buffer and then insert the pointer to that address.
Okay, so let's forget about the bin sh, like a's over here. So we want what? /bin/sh. 1, 2, 3, 4, 5, 6, 7. So I need then 7 fewer a's over here. And oh, it's still the same thing.
You didn't insert the pointer to that as the.
Oh yeah. So how do I find that address? Jump EAX? I might be able to jump to EAX. I don't actually know where I am in the program. I mean, yeah, it must be in string copy. It must actually be in EAX. So we could do that, right? Let's just see if we have MSF, elfscan, target. That could be a fun way of doing it. It's not what I intended to do. I was just going to jump to the system directly, right? Actually, no, we don't want to jump to EAX because we can't execute the code that's in EAX. It's a non-executable stack. So that's not going to help. So we're still stuck with going to system, but we haven't provided something very crucial to system.
Do you use an EIP minus a certain number, like 144, would that work?
144, what do you mean?
Like 144 bytes before the EIP. So that points to the beginning.
Yeah, but so far I haven't even provided an argument to system, right? I want to keep overflowing here. I want to say CCC, and I want to provide my argument, right? What is my argument? Well, let's just put ABCD here for now, and let's just see what the core file says. Target, core 32409. Whoa. Oh, yeah. Okay. Here, actually, what happened, which is very curious, is that system tried to execute, and it didn't find anything at this address, but it didn't crash for whatever reason, because it was already, it forked off a program. That program must have crashed, and it came back. And then it was done with system. So when you're done with system, what do? You pop the next address from the stack. You return to it, and now it's this address, CCC. So that's where it crashed. But we still have a chance to execute a real thing. So let's actually find where, in this core file over here, let's find where our bin sh string ended up. So how do we do that? Examine, say 64 bytes. What do I want to do? I don't think anybody can look further away from me. Totally, I'm right here. Maybe some register, like ESP, we do that. Some of this looks familiar. Look at the first 4 bytes. Maybe somewhere further down. Anything look familiar? Anything look familiar? Something looks familiar? Anything look familiar now? Look at the 4 ones, 4 ones, 4 ones, which should be like, oh, that's my stuff, right? Instead of looking at it byte, let's look at it in strings. Okay, let's do a few. Let's do 20 strings. Oh, here we have bin sh, then an A here. This looks a little familiar. Yes? Good, okay. Now, what's annoying about this is actually the stack is not randomized. Okay, just because we have a little time, I'm gonna turn off the randomization part. Because it's just, it adds an extra step, which we can do, but we're just not gonna do right now. 1, no, that makes it 0. Okay, so let's run this again, get another core. 7844. ESP minus 128, 256. Where does our thing start? We're looking for business H, which we know the slash is 2F, right? So let's try to find this. Anything look familiar? Ooh, slash bin slash sh a. Okay, we have located it. Now this looks like a pretty daunting thing. We have to find exactly the right location, right? That doesn't sound right. Let's try it regardless. So it's D4 AC. So OX D4, sorry, AC D4 FF FF. Oh, we were even off by 4 just from that. Because I added 4 more bytes, I think. AC. Oh, it's right. It's actually B0. So what's wrong now? It's trying to execute slash bin slash sha. What? There's no null byte, right? Oh, but we can't get a null byte in there, can we now? Oh, this is terrible. What could we do? What could we do?
Could you put the bin sh at the very end of your exploit string?
Yeah, where it necessarily has to
Yeah,
have a null byte, right? It's just that those things tend to be where our things are, right? We could possibly put it after all our arguments. It's not a bad idea.
Why can't you just add a null byte where instead of the ASLR version?
Because then we would stop in string copying all the exploit code, and then there wasn't an overflow to begin with.
What if you replace the A's with spaces?
Oh, it's not a bad idea. Let's try that. Let's just put in spaces here and see what happens. Spaces. Yeah, because when I do that, it thinks this is several arguments. So let me force the Perl script, let me force target to think it's a single argument. And now it's going to go like that. Okay, so that didn't fail. There's something very annoying about the fact that I have to hit the exact address. We had this nice NOP-SLED concept, right? But can we have something similar here? What if I, instead of doing this, having this 136 A's over here, what if I just had a bunch of slashes at the beginning? What do you think? Let's have that 136 minus 7, that's fine, and then our bin sh string over here. So what are we doing now? So now I can hit anywhere in this slash territory, except obviously something is still wrong. What's wrong? How about a semicolon? What does the semicolon really do? It delimits multiple commands. If I put a semicolon in here, it should try to execute that and not the other command. It will try to execute that later and it's going to fail, but for now, things will fail. So why did they fail this time? We have all these slashes. Maybe the whole thing is too long. So let me just make that shorter. So we're going to put that to be 36, and then we're going to add A's here for the remaining 100. Did that work? It did not work. SH is trying to execute all stuff. Everything goes bananas here. 16, 20. Ooh! We have a shell. What was happening? Well, it's possible that the stack frame of system was overriding our own buffer, right? Because we had our own stack frame where our buffer is, and then system started executing, and it thinks it has the same stack frame, so it probably started messing with it, right? But we were able to execute a shell. That's really cool. Now, coming up next, we're in the shell, and it's supposed to have this amazing thing called target over here, and it's root. I could actually execute this. It's identical to the other one. And if I just change it to uppercase target over here, it's gonna give me root privileges. Or is it? Oh no, I am still me. Remember the thing with how SH is annoying? Well, tell you what system does is that it runs /bin/sh minus c, whatever it is that you typed. So it automatically runs everything through that shell. Oh no, unless we've called something called setuid to set our privileges. So next up, let's see if we can go a little bit further and execute it the whole way. Sounds good? Okay, I'm releasing a new homework today, so stay tuned for posts on Piazza and stuff on the website. Cool, thanks.